Good day everyone. Welcome to another video of this lecture series. And in this particular video, we are going to discuss about the segmentation. Okay. So as we have discussed in the last lecture that our aim, or we can say our main focus, is to implement virtual memory. Okay. And we have already discussed one option, that is option 1 in our last lecture. The solution that we have discussed in this particular option is not implemented anywhere, but yes, it is one of the solution. Okay. Segmentation is another approach of implementing virtual memory, or we can say it is a mechanism of mapping the virtual memory of different processes onto a physical memory. But for implementing segmentation, we need some hardware support. Okay. What kind of hardware support? For example, we require some registers. So what are those registers? I will let you know. We require some registers. Okay. So what is segmentation doing? So basically we have a process, and for this particular process or any other process, let's suppose process 1 and process 2, we have it as virtual memory. Okay. And this is the virtual memory of process 2. And what is the virtual memory of process 1? For example, at the bottom it is header, then we have the code section, which is also called a text segment, and then we have the data, BSS, we have the stack, we have the heap. Okay, these are the different segments. So what segmentation says, that for every process, divide this process's virtual address or logical, it is also called a logical address space, into segments, and these segments may vary in size, they may have different size. Okay. For example, I will divide this process into segments. Let's say header segment is one segment, text segment is another, data segment is another, stack segment is another segment, and heap segment is another segment. Okay. Then what we are going to do, we will map these segments onto the physical memory. Okay. What does that mean? Let's suppose I have to map, I will take the text segment. So let's say I have the text segment of process P1. What I am going to do, I will see, let's suppose the size of this text segment is, let's say 2 MB, for example. Okay, fine. Or you can say it starts from address X in virtual memory to address Y, from X to Y. So what is the size of the text segment? The size of the text segment will be Y minus X bytes. Okay. Now we have to place this particular segment into a physical memory. In this physical memory, so, or we can say main memory, we will find a space which is of size Y minus X bytes. So let's suppose there is this space that is available, and this particular space can occupy these bytes, these or more than these bytes. And let's suppose the address of this starts from A and ends to B. So I am taking this particular segment of process P1 and I am placing this into this particular segment of main memory. So we can also say that this X is mapped to A, this virtual address X is mapped to A, and this virtual address Y is mapped to B. Likewise we do for other segments, but we have to store this information. For example, we have to store, if this is our segment, this is our text segment, where have we placed this text segment in the main memory. So this we have to keep in mind, where we have placed a text segment in main memory, or we can say we should know the starting address of this particular segment in main memory. So what it is starting address? It is A. So it is also called the base address of this segment. Okay, and the size of this, the total size, that is b minus a, is called a limit. So using the base and limit, we can say which memory in the physical address space or in main memory is allocated to the text section. Likewise, for example, data section will also have base and limit. Stack segment will also have has it as base and limit. Okay, so let me repeat it. What we are doing in the segmentation, we are in segmentation we are dividing the virtual address space, or we can say virtual memory map of a process into segments. Okay, then we are mapping these segments to main memory. And for a let's suppose for a process there are multiple segments. For example, one segment is called a text segment, or it is also called a code segment. Another segment is stack segment. Another segment is data segment. So there are different segments possible. Okay, let's suppose I am placing this particular segment into main memory, but I should know where in main memory I am placing this text segment. And the starting address of that segment in main memory is called a base address or base, and the total or we can say the length, the size of that segment is called the limit. Base and limit. Okay, so the starting address will be base and the ending address will be base plus limit in main memory. So these are the addresses of main memory. Now likewise, stack segment will also have its base and limit. Data segment will also be having its base and limit. Okay, so this is for process P1, let's say. Likewise, process P2 will also have text segment, stack segment, data segment, and other segments. The segments that are mapped into the main memory, for those segments we have to store their base and limit. And this base and limit of different processes is stored in a special table which is called global descriptor table. Okay, so global descriptor table. So basically you have to remember that we have global descriptor table per process. Okay, so let's suppose this is a global descriptor table of process P1. So it will have entries like this. It will be having multiple entries, and each entry stores two important things. One is the base, another thing is limit. And there are some other bits stored, but we won't discuss those bits. What are those bits? Those are also called permission bits, but we are not going to discuss about those bits. So it is storing base and limit. Likewise, this entry also stores base and limit. So let's suppose the address of this entry is A, the address of this entry is B. Okay, so At address A, we are storing base and limit. But whose base and limit? For example, if text segment of process P1, I am storing at some memory location and it is base and limit is limit. Then I will store this base and limit into the global descriptor table. So let's suppose text segment of process P1, I am storing into the main memory and the base address is B and the limit is L. I will store this particular entry here, base limit. Okay, but I should know that this particular entry belongs to the code segment, or we can say text segment. How will I know? Basically, in our, as I have already said, that for implementing segmentation we need some special registers, and one of the special register is called CS register, which is also called code segment register. This particular register stores the address of this location. Okay, so the code segment register stores the address of that particular entry in the global descriptor table that stores the base and limit of code segment or text segment. Okay, likewise we have a data segment register. This register stores the address of the global descriptor table that stores the base and limit of the data segment. Okay, likewise we have stack segment. We have different other registers. ES, this is also one of the register. So let me repeat it, what we are doing. So I will explain it for one process, you will understand it for other process also. So let's suppose I have a process P1 and it is segments like this. So it is the virtual address space from 0 to, let's suppose 2 raised power 32 minus 1. Okay, and this is our main memory. Fine. So I have divided it into segments. This is the code segment. So let's suppose its virtual address is V1 and it is top of virtual address is V2. Okay, and this is our data segment, or we can say stack segment. Stack segment's address is let's suppose V3 and end is V4. Fine. So let's say I am placing these code segments and stack segment into the main memory. Okay, in the main memory. So first I have to place this code segment into the main memory. Okay, so I will find some space in the main memory. Let's suppose I got this space where the starting address is A1 and the ending address is B1. So I will take this particular code segment and I will place it into the main memory. So what is the base address for this code segment in main memory? Base is A1. And what will be the limit? Limit means the size of the segment. That will be B1 minus A1. Okay. Now for this particular segment, I have to store this base and limit into the GDT of process P1. Okay, so this is the GDT of process P1. Okay, what I am going to do, let's suppose I am finding this is, let's suppose this is address G1. So I am finding this entry is free. So I will place A1, it is the base, and B1 minus A1, that is the limit of code segment here, and I will store this address into the code segment register. Fine. Likewise, let's suppose stack segment is placed here, whose starting address is A2, ending address is B2, and I have placed stack segment here. Here I have code segment. Okay, then in the here I will find another entry in the GDT. I will say that A2 B2 minus A2, and let's suppose G2. So it is the base and limit of stack segment, and this address I will store in a special register called stack segment register G2. Fine. Okay. Now let's say there is another process P2. P2's, let's say, code segment. I have placed, for example, this is the main memory. I have placed at this address. This is the code segment of P2. This is the code segment of P1. This is the stack segment of P1. Okay, so this is the GDT of P1. This is the GDT of P2. So in the GDT of P2, let's suppose there is some entry. Let's say this is the entry where I have placed A3 B3 minus A3. Okay, fine. And this particular address, let's suppose G1. So this is G1 here, or G5, address G5. Now I have to store this G5. This is the code segment of P2, and just G5 I have to store in the code segment. But in code segment I already have G1, where G1 is the code segment of process P1. So how will I store G5? Okay. Now let's see how we are handling this situation. What we are doing when our processor is executing a process, so let's suppose it is currently executing process P1. Okay, then these segment registers will contain the GDT addresses of process P1. However, if it is running process P2, let's suppose it was running process P1. So what we are there in the segment registers, it contains the addresses from the global descriptor table. However, now if it has switched from process P1 to process P2, so this is also called a context switch. Now it has made a context switch from process P1 to process P2. What our processor is going to do, it will store these values G1, G2 and other segment registers related to process P1 into the main memory for some time. Okay, it will store these values temporarily into the main memory. So in main memory, for every process there is, so in the main memory we have one table which is called process control block. Okay, in the process control block we have, so it is kind of a table. So in this table there is an entry for every process. Now if I am making a context switch from process P1 to process P2, so I will store the segment register values of process P1 into its entry, and I will get the segment register values of process P2 from its entry into the segment registers. Okay, that is how I am breaking this kind of time. Okay, so now let's see if currently my process P1 is running. So let's suppose, so whose GDT is in use, so that means we are using GDT of P1. And what will be in the segment registers, code segment, stack segment? In these registers it will contain the address of GDT entry that contains code segment of P1. So it will contain the address of GDT entry that contains the stack segment of P1. Okay, Now let's suppose P1 tries to access some address. Oh, let's suppose address is like this. This is 32 bits. It wants to access this particular address. Okay, so what my memory management unit is going to do, this MMU, it will divide this address into two parts, the first part and the second part. Second part will be the offset. Okay, and this part determines the type of segment. So let's suppose P1 has generated an address and this particular address belongs to a code segment. So which segment? Code segment. So basically we have to convert this particular address. This is a virtual address. We have to convert it into physical address. Physical address means address of a main memory. So my P1 is generating an address like this, and my memory management unit is dividing this into two parts. First is the segment ID. It tells the which type of segment this address belongs, and the second is the offset. Okay, so let's say it is saying that it tries to access the code segment. Which segment? Code segment. Then what it is going to do, it has to find, my memory management unit has to find the base address of this code segment in main memory. And how can I find the base address? I can find the base address in the GDT. But where in GDT? Okay, so that means I need that particular entry of a GDT where I have stored the base and limit of this code segment. And how will I know that particular entry? I will have stored that particular entry into a special register which is called code segment register. So from this register, I will get the address. I will get the GDT address. Okay, and from that GDT address I will get the base and offset. Okay, let me write it again. Let me write the complete procedure. So let's say this is our process P1. Okay, and this was its virtual memory. Let's only discuss the code segment right one. It is virtual memory 1 to virtual memory 2, and this is the main memory. So let's say in main memory this particular segment is mapped here, A1 to B1, and this thing we will have stored in GDT, this mapping, this base and limit. So base will be A1 and limit will be B1 minus A1. And this particular address, this entry, I will be having stored in the code segment register, this G1. So now let's see. Let's say process P1, it generates an address. Now comes the working of a memory management unit. It will convert this address, this is a virtual address, into physical address. So it will convert it into two parts. One part will be the segment ID and second part will be the offset. Segment ID is basically telling us to which segment this particular address belongs. So let's say it is saying that it belongs to the code segment. Okay, and we know that this code segment, this particular code segment is mapped at here. But we should know where from we will get this mapping. We will get this mapping from GDT. Okay, and GDT, I have to find this address, and this address is stored in the code segment. Here I got the information that this address belongs to the code segment. So from here I will access code segment register. From that register, I will get the entry where the base and limit of this code segment is stored. So I will get the base A1 and the limit. Limit is B1 minus A1. Okay, so this is base. So let's suppose this address was here that I needed. It was V1 plus 6, let's say. So in the main memory, it will be A1 plus 6. So it will be here. Because V1 is mapped to A1 and the distance here is 6. Okay, so here also it will be 6. So it is kind of an offset. Offset means the entry of an item inside some segment. Okay, so this offset is 6. We already know. It is from the address itself. Now I got the base. I will now to this base I will add this particular offset 6. That will be our physical address. So that is how we are converting a virtual address into a physical address using these segment registers and this GDT, global descriptor table. Okay, and also we will check one thing, that the address that it is trying to access, this address should not go outside this particular limit. Because if I am going outside this limit, so that means I may access the data segment or code segment of some other process. So before doing this, I will check this particular address A1 plus 6 or A1 plus offset. It should be under this limit, under this segment. Okay, A1 plus offset should be less than A1 plus limit. Okay, so if it is greater than this, we will raise an exception. Raise an exception means that we will inform the operating system, or we will inform our system that there is some unwanted access. Okay, fine. So we have handled both the security issue here. One process won't be able to access the segments of the other process. It can only access its own segment. Okay, so this is how segmentation implements virtual memory. Okay, so let me summarize it, what we are doing in the segmentation. So this is the summary. In segmentation, we are dividing the process's virtual memory into segments, where the different segments are, for example, the core segment, data segment, stack segment, heap segment, and many other. Some of these segments are mapped into the main memory. And for every segment, we will have a base and limit register, limit values. Base determines the starting address in main memory where this particular segment is stored, and limit gives us the size of that segment. And this base and limit values of these different segments are stored in the table which is called a global descriptor table, and it is per process table. So every process will have its own GDT. Okay, fine. And where, for example, for code segment, we may be storing the base and limit at one particular entry, and the address of that entry is stored in the registers. And what are the different registers? One register is code register, data register, another is code segment register, data segment, stack segment, There are many other registers. So what are these registers? What are they storing? Address in the GDT where the base and limit of that particular segment is stored. Okay. And you have to remember, if currently I am running process P1 is running, so these segment registers will contain values related to P1. Now if I make a context switch means that P1 is not now running, P2 is running. So what I am going to do, I will take the segment registers of P1 and I will temporarily store them into the PCB entry of P1, and I will get the segment registers of P2 from its PCB entry and store those into the segment registers. Then I can run process P2. That means then using these registers, now I can access the global descriptor table of process P2. And how we are changing virtual address to physical address? So this is the virtual address. Virtual address is divided into two parts. First gives us the segment ID. The second part is the offset. From the segment ID, we get the segment register. We access the segment register. From that segment register, we will access the global descriptor table. From that global descriptor table, we will get the base. And to this base, we will add the offset, and that will be our physical address. But we have to make a check that this particular offset is within the limit, or we can say this offset is less than limit. Okay. So this is how segmentation works. And with this, we have completed how we can implement segmentation, or we can say how we can implement virtual memory using segmentation. Fine. Now there are some limitations associated with the segmentation itself, and that forces us to change from segmentation to other schemes. So what are the limitations of segmentation? So let me write the limitations. Limitations of segmentation. So one important limitation is fragmentation. What does that mean? Fragmentation. For example, in main memory, so let's suppose my code segment was of 2 MB. Okay. And in the main memory, there is a space available which is 2.5 MB. So in this 2 MB, I will map this particular code segment, and how much space will be wasted? So 0.5 MB space will be wasted. So this is the fragmentation. Another problem is the process growth. Let's suppose we mapped stack segment of a process into the main memory. So here I have mapped the stack segment of a process. So there is a possibility that this stack segment may grow, because stacks grow and shrink. Both heaps also grow and shrink. So there is a possibility that the stack may grow. And let's suppose after this particular stack, we are having code segment of some other process. Okay. So now stack segment grows. So let's suppose here also we have code segment of some other process. Okay. Now if I have to increase the stack segment, so that means I have to remove one of the segments from here, either this segment or this segment. Okay. So that means if there is a process growth in the segmentation, then there is a possibility that we may have to relocate processes. Or I can say, for example, I may have to take this stack segment to some other place where the space is available for larger size. Okay, so that is another limitation of segmentation. So because of these limitations, we are moving from the second option to the third option. And what was our option third of implementing virtualization, or we can say virtual memory, is paging. But before discussing paging, you have to keep in mind that for implementing segmentation, we need some hardware support. Hardware support in a sense, for example, my processor should have segment registers. Okay, because I will be using those registers. Okay, now as I'm saying that because of these limitations, we are moving from segmentation to paging. I will discuss this paging in detail, but you have to keep in mind that in most of the processors, they are using both segmentation as well as paging. So there are segment registers in almost all the processors, but now processors are coming up where they are not using segmentation, they are only using paging. But the older processors are using both segmentation and paging. First we are using segmentation, then after that paging. Okay, so let me discuss paging. So as I said, paging is a technique like segmentation to implement virtual memory. Okay, and what is this technique? Let me discuss it. So what in paging, what we are doing, we are dividing virtual memory of every process into fixed size blocks, and these blocks are called pages. So the virtual memory of every process is divided into fixed size blocks called pages. And also the main memory is also divided into fixed size blocks, but these blocks are called frames. Okay, pages and frames, they have the same size. For example, if it is of 4 KB, this is also of 4 KB. So what I am saying in paging, what we are doing, so in paging, let's suppose I have a process P1 whose virtual memory was like this. So we are dividing it into fixed size blocks, which are called pages. So this is page 0. Page 0 of process P1. So it is starting address will be 0. And the ending addresses, let's suppose every page is of size 4 KB. So the last will be 4 KB. Likewise, other pages. Okay. So this is the base address of page 0. Like in segmentation, we were having base address. Here also we will have base address 0. We don't have to store the limit. Why? Because for every page, the limit is 4 KB. Or we can say the size is 4 KB. Likewise, we have to do for the P2 also. We are dividing it into pages. It will also have its own pages. Page 0, page 1, page 2, dash, dash, dash. So let's suppose I have a 4 GB virtual memory. Then how many pages will be for every process? It will be 4 GB divided by 4 KB. So it will be 2 raised power 20 pages for every process. 2 raised power 20 page. And in page 0, for example, in page 0, how many bytes are there? 4 KB bytes. Okay, so now I have these processes, and I have a main memory, and I will divide this main memory. Let's suppose this main memory is of 2 GB size. I will also divide this main memory into different fixed size blocks, which are called frames. So this is frame 0, this is frame 1, this is frame 2. Okay, so how many frames will be there? So the frames will be 2 GB divided by 4 GB. That will be 2 raised power 19 frames. Then what I am going to do, I will place the frames. We will place, or we can say we will map the pages of processes into frames. Okay, we will map the pages of processes into frames. For example, let's say in frame 0, I am placing page of process 1, page 0 of process 1. Let's suppose in frame 1, I am placing page 0 of process 2. Okay, so basically we are placing here the data. Fine. Now one thing we should know, or we can say one thing we have to store where this page 0 of process 1 we have stored, or we can say we have mapped to which frame. Okay, and that particular information is again stored in a table which is called a mapping table. So we have a mapping table, okay, for every process. So this mapping table will be indexed by the page number. So it is indexed by the page number. Okay, so this is mapping table of process P1. Let's say page number matlab means that if I have, this is page 0, it means page 0 is stored at here. In this location we will store the frame number where this page is mapped. Okay, what I am saying, let's suppose I have page 0 at here at frame 2. This page is at frame 2. Okay, and I will have address F2 here, frame 2. Let's suppose in this page, in page 0, I require a data item which is at location 10th location in this page. So what is it as offset? Offset is 10 here. So in page 0, I will require the 10th byte. 10th byte. So now I have to get that byte from the main memory. So in the main memory, I will first find out where this page is placed. And how can I get that information? I can get that information from the mapping table of P1. So I will see this page is stored at frame F2. So at this frame. And in this frame, which byte I have to get? 10th byte. Okay. So F2 plus 10 gives me the physical address of that particular byte. And this mapping table is also called page table of process P1. You can see that every process will have a page table, and these page tables are also stored into the main memory. Fine. So let me repeat it again. So let's suppose I have two processes, P1 and P2. Okay, it will have it as pages. How many pages? 2 raised power 20. This will also have it as pages, 2 raised power 20. And we have frames, or we can say we have main memory. And how many frames are there? 2 raised power 90. So this P1 will have its page table. Okay, page table will be like this. So how many entries will be there in the page table? In the page table there will be entries. So we already know that the entries are or we can say it is indexed by the page number. So how many pages are there? 2 raised power 20. So entries will be 2 raised power 20. And what is every entry storing? Every entry is storing the frame address. So how many bits are required for the frame address? 19 bits. So every entry stores 19-bit value. Likewise, P2 also has a page table. Okay. So some of the frames from P1 are placed into the frame, into the main memory, and those frame numbers are mapped into the page table. Likewise, the some of the pages of P2 are stored into the main memory and other pages are into the secondary storage. Okay, and this is how paging implements virtual memory. Now we have to see how these page tables are accessed, or we can say how our virtual address is converted into physical address, because that is our main aim. Virtual address convert into physical address, and also we have to find out how their address spaces are different. So regarding those things, paging, page tables, what are the different types of page tables, we will discuss those things in our next lecture. Till then, goodbye.